during the flight you are not allowed to hook up the internet, and also cannot take picture or video. So we still need to wait till final grade for the first 3 months.
程式更改了，操作错误，所以 keying 成绩就打出来。
这一届把它做的更复杂、更人性化，可是就变成说它有一些资料漏输错的，就是因为昨天也发生过，就是有些题目是错的，对我们名字是错的，就
只有3个题。
那里，保影片那边会有。
就是反正第一就是像题目 number 10，对，第一个题目，第二个题目，
对对对，就三
先
3个。就写号码就好。
写号
照着上面。
对，写一下第一个放置次第一个是number 10，然后15，然后对，你先写10，这是第一个。你听懂我意思吗？对，你就写 problem number 10。
那我看我先分出来。我不晓得需不需要我分出来你那边2个，那我就写我先被关掉。
你被关掉。
然后，
不好意思，那个我们分数好像有点意思。
我实力付入。
我想他们帮他们说他们分数有问题，我想那个我们先不管那个了，我们
分数之后再找。
之后再找那个。
会影响排
会影
名。
响。
我没办法处理。
他先起来。Okay, sorry for the late, and I think we are ready. So we will start this the final round of this fight. Okay. As a start, I want to ask each team captain to introduce your team and the team member. Okay. We start from the reporter, please.
Hello everyone, our team name is MD Fresh. So my name is Cho and he is here at home. Zhang Pingqi, Dale and Sean. Thank you.
Okay, opponent, please.
Hello everybody, my name is Jonathan Bruce. I'm captain of Team All-Nighters from Taipei American School. These are my wonderful numbers, Richard, Rupert, Daniel, and Austin, and we are really excited to debate with you this afternoon.
Okay, and the viewer, please.
Okay, so hi everyone. My name is Ian Zhang and the team leader from Windy, and we are from Kaohsiung Senior High School. And our members Fang Youjun, Chen Meijun, and Yang Zhanyu. Thanks.
Okay, thank you. Now I want to introduce the juries, start from myself. My name is Qian Hua Bao from Zhongzheng University. Then, please.
My name is Su Benhu. I'm from National Taiwan University.
My name is Yan Zhenxun from National Central University.
I'm Wenjun from National Taiwan University.
from Cambridge University. From Chengdu University.
Okay, thank you. So, the first problem is the problem has two choice. So the first five, the problem is number 10.
Number 10. On top.
Okay. Number 10. I want to ask each team write down the presenter name on the blackboard, and so the reporter will have 5 minutes to prepare.
Hi.
reporter, please.
Hi everyone, I'm Sean from Team MD Fresh, and today we're going to investigate problem 10, conducting lines. As stated by content statement, a line drawn with a pencil on paper can be electrically conducting. Investigate the characteristics of the conducting line. So the problem statement asks us to draw a line on the paper, which is conducting, and investigate the characteristics. We have 4 parameters: the length of the line, the width of the line, the carbon content of the line, and the temperature of the line. And from our task, we can conclude that it has focused on conducting graphite investigation, pencil-paper interaction, and characteristics that affect resistance. So first, we're going to investigate, introduce the phenomenon, then the experiment setup, then the theory, and then the experiments, and comparing our data analysis against our experiments. That's the conclusion. So, phenomenon, as you guess, phenomenon, video. So as you can see, when placed on the multimeter on the conducting line, you can find a value, which is the resistance. First, so we need to first determine why graphite is conductive. In the graphite structure, graphite is made of a covalent bond of carbon, and each carbon provides 4 outer electrons to structure the graphite. And 3 of the electrons are localized electrons, which connect and form each layer and have strong connection between them. And the localized electrons are used to connect each layers together, which means that they can freely flow between the layers. And this is why graphite is conductive and is ohmic. So since we applied pencil on the paper, we need to investigate the interaction between the paper and the pen. So you can see as we put the paper under a microscope, you can see that actually it's our uneven surface on the paper and made of fibers. And the side view, you can draw a side view of the fibers of the paper, and you can see there are grooves. And when a pencil is drawn over the grooves, the kinetic friction between the pencil lead, and the grooves of the paper, which scrape off graphite, which graphite will then inside the grooves of the paper. So our experiment setup for our cross-section area, we are determining the width, and we use a 3D printer mode which controls accurate width of the line. Then the length, we use a vernier calculator, electric vernier calculator, and have which various lengths. Then for our graphite content, we use 2B to 5B pencils, which specific graphite content. And for temperatures, we have put the pen thermometer onto the line and testing the temperature, in which our surroundings are include fridge, room temperature, and heating rate. So here, as force, according to literature, Rochester Institute of Technology, as force applied on paper, actually there is a shear force between the lead and the grooves and the grease part grooves of the paper. So when after a certain amount, the shear force smoothens the grooves, so which lastly the grooves of the paper will be truly smoothened down for each kind of paper as when a certain stroke is applied. And over the stroke, since the intermolecular force friction force between the graphite layers are too small to withstand more applied graphite, so the graphite will fall out, which cannot stick on the graphite anymore. Next, so since the contact layer is ohmic, so we can apply the resistance formula. And for our length, you can see as this is that there is a positive correlation between the length and the resistance. And for our cross-section area, since our depth is constant throughout, we change the width. So as width increases, the resistance actually decreases. So it's a negative correlation. So Actually, in lead, in the manufacturing lead, the manufacturing factories actually combines clay and graphite to form lead. So we have 2B and 5B pencils, and since different factories have different percentage, we are able to calculate the carbon content for each pencil. So as when 2B has lower graphite content, and which has a higher clay content. So the graphite content and resistivity. So this is a formula of which we can derive the lead resistance, and by applying the clay resistance from literature, we can calculate our graphite content from our tested resistance. So you can see as graphite content increases, since the resistivity, it will cause the resistivity to decrease, which cause the resistance to decrease. So here, according to in local temperature, about 0 to 450 degrees, graphite acts like a semiconductor, since which means that as temperature is provided, the temperature is used to provide the energy to make the electron fall from the valence band to the conducting band. And we have an online source which provides the temperature coefficient range from online source, which we can use to support our upcoming experimental data. And according to literature, 0 to 150, there is a linear relationship between the resistance and the temperature. And at over 200, there will become curvature, and up to 600 degrees, the graphite will act like a conductor. So experimental data analysis first. So since this graph shows that applying to about 350 strokes, the resistance will stay to a constant value, which means that we can then derive the strokes into the depth of the line. Next page. So by applying over 350, so we can see that the depth of the line actually becomes constant. So we can say that our setup is very precise, and we are able to only change the width. So next experiment, the length of the conducting line, as you can see, as we increase the length of the conducting line, there is a positive correlation between the length and the resistance, and our values are very close to our theory. So according to width, since our depth is constant and we change the width by our 3D printed mold, you can see there is a negative correlation between the width and the resistance. Then the graphite content. So as graphite content, you can see over here, since for this there is no, we can't apply the theory, since the graphite content for each manufacturing is different, and from our calculation, we have calculated all the graphite content for all 2B, 3B, and 4B and 5B, and you can see as more graphite content is applied, the resistance decreases, and this means that since the clay resistivity is decreased in the components, so which means that there is a decrease in resistance. Okay, now, so here you can see in the temperature, since the problem states that the line drawn is on paper, and so our tested values are the values that the paper won't burn out. So it's under the local value, which is -6 degrees Celsius up to 450. So you can see as temperature increases, the resistance of the conducting line decreases. So there's a negative correlation between the temperature and the resistance under local temperature. and you can see we can input, and we are able to calibrate our temperature coefficient average for this point, and also decrease to this point, and both of these values fall in the range of from according to our fall into the theory range we provided previously. So in conclusion, to restate the wrong statement, a line is drawn with a pencil on paper can be electrically conductive. Investigate the characteristics of the conducting line. So we are able to accurately draw a fixed dimension by applying to a maximum strokes and by controlling the dimension of the conducting line with a 3D printed mold, and as length is directly proportional to the resistance, and our cross-sectional area, which we only alter the width, is inversely proportional. And our graphite content, which we are able to calibrate according to the tested resistance, and by applying with literature, we can calculate the graphic content, and we can find that it is inversely proportional. And lastly, as temperature increases, the resistance decreases, since under local temperature, graphite acts like a semiconductor. Thank you.
Pardon? Okay, next answer your question.
Okay, thank you for the great presentation. So I just have a couple of questions here. So first of all, just to clarify, in your experimental setup, you drew the lines by hand, right?
Yes.
Okay, so how did you standardize the amount of force applied pushing the pencil down?
So the force, we can neglect force because the force is only changes the depth cause, since we applied, we have an experiment which says that after 350 strokes, the depth of the pencil lead will come to a constant, and because since no more graphite will be landed on the line, so we can neglect the force since we already applied. So after over the
okay,
stroke.
Okay, cool. So in other words, you're saying that for the rest of your experiments, you exceeded that
Yes.
threshold
Yes.
for flattening the paper.
Yes.
Okay. And another thing is, did you vary the amount of pressure applied to the pencil for different grades of pencil lead? Because obviously, for example, 5B is softer than 2B, so you need to probably apply less pressure for like
So
5B.
it's the same thing. So actually, it's the same as we apply over 350 strokes. We approximately apply 400, so it will still have the same thing. And then we have calculated, so for all of since we have used the same type of paper, so the depth will be the same.
Okay, cool. And actually, a note about the paper. Did you test different types of paper?
No,
okay.
since our main focus in here, and we think that more in real life, we mostly use these kind of smooth papers, and
okay,
it's not closely related to the.
Okay, cool. And another thing, you mentioned that after a certain stroke value, the graphite deposit is not able to really attach to the paper. So in your experiment, did you like shake off this actual graphite?
We just take it out. Yeah.
Okay.
When you're drawing, the powders goes to the aside. Yeah.
Okay, cool. Thank you.
Okay, opponent has 3 minutes to prepare your presentation.
Hello everybody, my name is Jonathan and I'll be opposing number 10 conducting lines for the all-nighters. So let's begin with the problem statement again. So a line drawn with a pencil and paper can be electrically conducting. Investigate the characteristics of the conducting line. So my proposed model for investigating this problem is how is the conductance of pencil lines different from a typical conductor like a wire, and how do relevant parameters related to the line affect its conductance? So here are what I feel are the pros and cons of the reporter's presentation. So the reporter had good time management, and he was very clear in his definition of variables and parameters that he tested. He had a very clear experimental setup and was able to control many variables with that, although not some, as I will get to in my discussion. And he considered and tested many parameters, namely length, width, graphite content, as well as temperature. And he also attempted to control many of his variables, which I applaud him for. And as for cons, he did not provide any definitive proof that they reached this required force to flatten the paper in all their experiments and to basically ensure that the pressure being applied when writing the line doesn't really matter. And they also had a slightly questionable model for modeling the relationship between resistance and graphite content, which we'll also get to in the discussion. And lastly, I would have wished for more intuitive explanations of the phenomena and basically why what they presented actually occurs. So with that, here are the main points that I would like to discuss during my discussion. So the first topic is how did they account for the pressure applied to the pencil in the experimental setup? Because even though they attempted to provide reasoning during my questioning, I still think that this is a very important parameter. And I would also, again, like to reiterate how important they consider this to be to their results. And the second topic is whether they examined how the behavior of pencil lines differs from the behavior of a typical conductor like a wire. And also whether they have intuitive explanations for the relationship between resistance and, for example, temperature as well as graphite content. And topic 3, I would actually like to propose something that they could perhaps include to make their theory even better, which is a percolation model and actually finding a critical volume fraction for that. So with that outline, I would like to launch into the discussion now, if possible. Okay, so first I would like to return to the topic of pressure applied to the pencil. So I still feel that this is an important parameter to control in your experimental setup. So do you have any modifications you could propose to your experimental setup in order to accomplish this, to basically control the thickness of the line?
The thickness, you mean? So by applying, we have tested that also supported by the theoretical model. We tested that over 350 strokes. The resistance no longer increases or decreases, and by the resistance and tested resistance of the pen lead, we can derive by calculation and derive the by testing resistivity and derive the depth, which is the second graph. Yeah.
Okay, but since you didn't control the pressure which you used to push down the pencil onto the paper for each of those 350 strokes, how can we actually be sure that this threshold, let's call it, was reached for all your experimental trials?
Yeah. So we make sure that we use 400 times. So it makes sure since adding strokes won't affect the depth and anything. So according to our experiment, after 350, it will go to a certain value. So we applied about to over 400 strokes. So we make sure that each part of the mode will have the same depth.
Okay. And another thing, again, I would like to return to the pressure applied for different grades of pencil. So did you use, for example, more strokes for harder pencils to ensure that this threshold was reached? Because obviously you need to apply more pressure to a harder pencil.
For all of them, since it doesn't affect anything, so we apply above 40 450 strokes to ensure, and we did ensure that the depth are all constant.
Okay, so you agree that the stroke threshold is not necessarily constant between the different pencil leads, and you did account for this in your experiments,
Yeah.
correct?
Yes.
Okay. I still feel that the thickness is very important. So I suggest that you make a more controlled experimental setup to perhaps test this in a more controlled manner versus just applying a certain threshold.
But we think if we already apply the force over the maximum source, we think that it's really we really did a precise job since.
Okay, so I get that when you tested length and width of the line, for example, you applied this threshold value. But in terms of actually testing the effect of thickness on the resistance of the line, I think that you could use a more controlled set to do this. So for example, you could, to ensure that the correct amount of pressure is applied to the pencil, you could, for example, mount the pencil on sort of a sliding apparatus like this, and then have a mass on top, basically pushing down on the pencil and sort of draw over it. And the more times you draw over it, that of course varies the thickness. So I think that you could perhaps incorporate this as a more accurate method for testing the effective thickness on the resistance.
But we still think that it doesn't matter since we already achieved the maximum stroke, so it definitely gets to the depth we wanted. So I think that both of these are both applicable for this. So I think these.
But then you're suggesting that thickness is not really an important parameter then, because you're just saying that once you reach that critical thickness, that doesn't really matter.
We must reach the critical thickness since actually the grooves in the paper are not unified yet. So we must control the depth.
Okay, but my question is, then in that case, how isn't it still important to test thickness as a parameter? Because of course the thickness of the like essentially film of graphite deposit on the surface should affect its resistance. Right?
Yeah, but it's hard since the grooves are different. If you apply the thick in each groove, the thickness will be different since the grooves are different. So I think it's not applicable for this. So we choose to use it with and control very precisely of the depth.
Okay, well I still think since this is a thin film resistor, you should consider thickness. But anyway, I don't want to dwell too much on that. I'd like to move on to the other topics of my discussion. So I would also like to ask you, how did you examine how the behavior of these pencil lines was different from the behavior of a typical conductor like a wire? Because of course these pencil lines are not made entirely of a conducting material. As you mentioned, there's some clay in them. So did you notice any major differences between the behavior of the resistance?
You mean like for pencils, since there are different carbon contents inside, so we use different hardness pencil which alters the clay and carbon percentage. And as we found out, as the carbon content increases, there is a decrease in resistivity, and which since for wires it's only a element.
But I mean, like what I'm asking is, so for other factors as well, I mean, like with regard to temperature or length, width, you're saying that these pencil lines behave a lot like a wire despite having essentially completely different.
So wire is, I think you need very which kind of wire. Since for most wire there are conductors. But in local temperature, since it is drawn on paper, in our experiment and also surveyed by literature, the graphite acts like a semiconductor. Okay. So it's different. One is semiconductor in local temperature, 0 to about 150 degrees, and then for wires they are conductor, which one is inversely proportional to the resistance, and one is oppositely proportional to the resistance.
Okay, and actually about that, interesting to bring up temperature again. Can you go back to that slide where you show the temperature dependence?
Yes.
Okay. Okay. Now, typically for normal wires, as the temperature increases, the resistance also tends to increase. So, can you provide a qualitative explanation as to why it's different in this case? Why the resistance actually decreases with increasing temperature?
Since this in local temperature, this is graphite, and graphite acts like a semiconductor. Go to the derivation.
Okay.
There's a formula which states for
And since for graphite we have a range and the temperature coefficient range it's in negative point, so you can see as temperature increases there is a negative temperature coefficient which decreases.
Okay, but what I'm basically asking is, do you feel that you can provide an intuitive explanation as to why this is negative? I mean, I see that it's negative, but could you explain
Why it
for
decreases?
instance?
Yeah, for here,
quick explanation.
since it's a semiconductor, since the heat provided, since it's a semiconductor for semiconductor, the band gap between the conducting band and valence band is close, and the energy, instead of providing more collisions that is applied to conductor, instead in semiconductors the heat provided is energy to let electrons from the valence band transfer to conductor.
Okay, I feel that's a good enough explanation for now. I'd actually like to move on to my final topic in these last couple of minutes. So could you go back to the slide where you present your theoretical model for how the resistance depends on the graphite content?
Here.
Yes. So how are you confident that it is essentially a linear relationship there? Because you're essentially saying that the resistance is basically directly proportional. Are you confident that it is in fact a linear trend there with regard to the graphite content in the resistance?
Actually, for over here, you can see that it's as you increases it decreases. Yeah.
Okay, well my question is, since we envision this as a particle level, since the clay particles are pretty much randomly interspersed within the graphite particles, do you really think it'll be linear?
Actually, we research, and actually the clay is evenly distributed inside of it.
Okay, well, I mean, nonetheless, I think I can propose another modification to your theory to actually help with this, which is a percolation model.
Okay.
So a percolation model essentially models this at the particular level and focuses on essentially presenting the structure of the pencil line as a lattice of particles and finding paths through that lattice, which essentially correspond to paths which the electrons can travel through. And the percolation model would suggest something like this, where the conductance G, or the inverse of the resistance, is proportional to the volume fraction of graphite particles minus a critical volume fraction, which is necessary for it to conduct at all, to a certain exponent. So essentially what you're telling me is you have found this to be a linear trend, right? From your experiments or whatever?
So according to this your theory, it's a curvature? Or
Yeah. What I'm basically saying is a percolation model, which is typically used to model situations like these, would produce some sort of exponential behavior. So how would you reconcile this with your theory and experimental data? I mean, like essentially what I'm saying is, do you feel that I'm suggesting that you incorporate this as a part of your theory to sort of better explain the behavior?
But this shows a curvature, right?
Yes,
More of a
it
curve.
shows a
But
curvature.
from our experiments, shows more of the linear. So we think that according to our research theory and our data, we think it's better to do the linear. And we maybe can do a further research on this and also deeper investigation.
Yeah, because I suggest that you include this in your research because, for example, potentially for graphite contents beyond the range described in the graph, it might exhibit some sort of curve. Yes, I'd recommend that you include that in your theory to improve it. And that's.
Okay, please summarize the discussion.
Okay, so I feel that we had a very fruitful discussion. So first we revisited the point of pressure applied to the paper, and the reporter was confident that in all cases of his experimentation, he applied the required pressure necessary to basically flatten out the grooves in the paper. I would still like to see more mathematical proof of this, but for now I feel that this is a satisfactory explanation here. And we also examined how the behavior of pencil lines differs from the behavior of a wire, and the reporter provided an explanation of specifically why the temperature coefficient is negative. And the third topic is I proposed a modification to the reporter's theory to include a percolation model, and encouraged that he look at a wider range of graphite contents to see if there is in fact any curvature, and if that percolation model would actually hold true for his data. And I think that this is important to include in his theory. So, thank you.
Okay, reviewer, please approach.
Oh, sorry. So I have a question for reporter.
Yes.
You mentioned that when the height of the graphite comes to a certain height, and the density of it won't change.
Yeah.
So could you tell me what is the difference between 2B and 3B or graphite? Because if the height of them are the same.
It's the same. Yeah. For in the main factor of determining the depth is actually paper, but in our experiment, the paper is actually the constant. So since we already applied over 350 strokes, so the depth will be all the same, and no neglecting the pressure since we already achieved the over the strokes value.
Okay, I see. So could you please change your theory?
Which theory?
Which you have mentioned, electron, maybe.
Electron?
The graphite structure.
Oh yeah, graphite structure. Okay. So I think it's. Oh no. Graphite structure. Here. Yeah. Okay. Here.
So could you explain what's the difference between 2B and 3B, the structure of them? Because.
Oh, basically, this is graphite structure. So graphite structure, 2B and 3B, it's a lead. It's a mixture of clay and graphite. So, but in graphite, it's an element. It's a covalent bond of carbon. So it's not related with that. We just output graphite independently, which shows that we prove that it's conductive because of the free flowing localized.
So percentage of the clay in the pencil did not affect the experiment. So
Yes, yeah, it does affect the resistance, but this graph only shows proves that why the problem statement says that a conducting line is conductive because it contains graphite inside a lead which has free flowing electrons inside which conducts.
sure, and that's my only question. Thank you.
Okay.
Reviewer, you have 2 minutes to prepare your presentation.
所以是你这边扛错，很强，他是要看这边扛错。
这一层。
Review, honorable jury and distinguished presenters. I'm the reviewer from Team UD, and I'm going to review problem 10 conducting line. And this is a proper statement. The line draw with a pencil and on paper can be electrically conducting, and that is quite important. And reporter have to do such experiment and explain the relationship between them. Sure. And the phenomenon, the pencil line is a conducting thing, and the laws apply to it. So R equal to rho L localized structure and the localized electron review of the experiment and parameters, change factor, the temperature, and change the depth of the line which he has drawn, and also in 2B to 5B pencil, and they set up they have a paper, and they draw a line, and they use pencil to draw a line on it, and then they have taste its resistance. And the result, the more the drawn cone is the less the resistance are, and the higher the temperatures is, the less the resistance are. And analysis, they made a lot of charts to show the relationship between variable and resistance. And advantage of the reporter, the PowerPoint is clear and the reporter speaks fluently, and he has shown the great chart that let us can understand very quickly, and impressive experience setup. And the suggestion is the pressure on the pencil can be controlled more specifically, and because our opponent has a suggestion that they could put a mass on the pencil, so the force which provided by human could be well controlled. And the clash. So opponents say what to do, use to measure the pressure of a pencil, and reporters say hand, and there's a better way. So I've mentioned it before. And then how did you account for the pressure applied on a pencil in your experimental setup? You can consider this important to your results. And reporters say apply the graphite on surface, and when you come to a certain height, density, the height of it won't change. And the critical volume fraction and correlation model. So okay, so the reporter's answer is that the trend of the line is linear, but not a curve. So in my opinion, because due to the experimental results, I think it is maybe linear too, but reporter could do more experiment and collect more data, so we can understand, is it a curve or the linear line, linear function. The conclusion, the reporter has do very well experiment, and opponent has very precise questions to improve the experiment. So I think both of them are very good at discussion, and it is my pleasure to review their discussion. And that's all. Thank you for listening.
Okay, thank you. And concluding remark from the reporter.
Okay, so first, the opponent kept saying that they think that we should be better controlling the pressure, but in our experience, since we already achieved and oversized the minimum amount of strokes, which already makes our depth of the container very constant and very precisely, we don't think that we must use that kind of devices, which is more complicated for us. And for second place, since the problem statement is only focusing on the paper, and paper's burning point is about 150 to 180 heat degrees, and we think that over the ranges is not relevant to the problem statement. And so, which is why we found that in local temperature, the resistance is in linear form. And as I said before, so all the depths are calculated, and we found that for different, it doesn't it isn't caused by the various of hardness B's, 2B, 4B pencils. Instead, it's all affected by the of the surface roughness of the paper, which is constant throughout our experiment. So we can neglect the problem. And as we think that the correlation model, which raised by the opponent, may be a further investigating topic. But for us, we have a very strong and precise calculation of the which proves and supported by our data, which proves that in our range it is linear. Thank you.
Okay, thank you. Now, question from the jury. Yes.
For the report, could you turn to page 19? Is this a straight line or a curve?
I think that it's more to a curve over here. Yeah. But
Okay, so what we're used to do is
it's more.
put more data to show that
That
it's
is
indeed a
okay.
curve. It looks to me it's a straight line.
Okay.
For the opponent, we just wrote down an equation on a blackboard.
Yes.
Could you give us some physics for this equation?
Well, essentially, a percolation model again simulates the pencil line as basically a series of particles and focuses on finding the number of paths between contacting conductive particles, which are basically the paths that the electrons can travel through when traveling through the material. And the number of paths that the electron can take through the material is found to be proportional to the conductance, or inversely proportional to the resistance. So essentially what I'm saying there is that the amount of conducting particles per unit volume, so essentially the volume fraction of graphite in the pencil lines should have some sort of exponential relationship to the conductance, and that this exponential relationship can be fitted experimentally, because it really does depend on the experiment. But I'm basically arguing that it should not be linear as they found, it should be exponential.
So what do you expect the value of alpha? It's close to 1?
The value of alpha can be variable. I might expect that it would be close to 1, but again, I don't think it's exactly linear. I think that it should not be linear.
Question? Yes, please.
And the opponent you proposed that pressure is a critical issue in this experiment.
Yeah.
So I would like all three teams try to explain that how the pressure may change the conducting mechanism in this experiment. I mean, the pressure you apply.
Also on the paper. So since when you put the paper under the microscope, you can see that actually the surface confidence is actually varies, and the resistance is very dependent on how the pencil that is applied on the groove. So for our experiment, we can inject the pressure, since we can ensure that the depth of the conducting line is constant. So, and you said if pressure, and with more pressure applied, the more of the graphite will be straight up by the grooves, and which can have more in the grooves. But in our experiment, we have flattened the grooves, so which makes the depth of the conducting line constant.
I do find the reporter's point valid about the grooves, grooves present in the paper. I do think that the pressure is very relevant, because if not enough pressure is applied, then there might be some very, very small gaps in the line where essentially the pencil goes like in and out of the grooves. So I think that that's very important for determining the conductivity. But also I think that moreover, if we just put aside the grooves in the paper for a second and just look at it as if the paper is smooth, then the thickness of the line should also significantly play a role in the resistance. So that by controlling the thickness with the amount of pressure, that could also be a significant variable.
Okay, I have the same opinion as the opponent, because I think the pressure might change the height of depth of the line. So I think the conductivity will be changed if the depth of the line change. So I think that's how pressure affects the experiment.
And one question for the opponent. You just proposed a population model, right? And you explained that. So I think that's okay for the thickness of the graphite is very thick, right? So, but if the thickness of the graphite is very thick enough, do you think the population model is still apply in this case?
Well, I do believe that the percolation model can be applied pretty widely. I think that what might change with that is actually the value of the constant, since that is very dependent on the conditions, and actually, quite frankly, should be fitted experimentally. So we might see the value of the constant alpha change, but overall, I feel that it can be applied to a much thicker line as well.
Okay, and so please go to page 21. How do you measure the density of the carbon?
Carbon content?
Yes.
Okay, so
21.
24.
21. This one. No.
Oh, that's right. Okay, so how do we measure? So basically, we find the clay, the resistivity of clay directly on literature, and by testing, we just put the multimeter on the pencil to test the resistance, and we can calculate all the dimensions of the lead inside, and we can derive a resistance.
2B is about 95%.
Yeah.
How do you measure that?
Measure the 85? Yeah. So we first measure the resistance of the pencil without sharpening, and since we have all the lengths, value, and the dimensions of the cylinder, so we can derive with the resistance law, we can derive the resistivity of the line, and then according to literature, we can have the resistivity of the clay, and by combining the clay plus the resistivity and timing the percentage, we can derive.
Okay, let's go to the plating part. Okay, let's start from the reporter. Which list you're supposed we start from the back. The 776777. And opponent. 677886. And then reviewer. Yes, please. 665766. Do you want to make some comment? No, okay. Then let's take 50 minutes.
It's up to you.
Okay, because we started a little late, let's take a 10 minutes break. Let's start the second part. So I want to ask each team, please write down the name of the presenter on the blackboard. Problem number 15.
你这样就就是I'm ready to begin the presentation. Okay, so hello everybody. My name is Jonathan, and I'll now be reporting number 15, pepper pot for the all-nighters. So let's begin with the problem statement here. If you take a salt or pepper pot and just shake it, the contents will pour out relatively slowly. However, if an object is rubbed along the bottom of the pot, then the rate of pouring can increase dramatically. Explain this phenomenon and investigate how the rate depends on the relevant parameters. So we identified 3 key research focuses from this problem statement, explaining why shaking and rubbing affect the flow rate and the differences between shaking and rubbing, modeling how rubbing specifically impacts the flow rate using kinetic energy of the particles in the pepper pot, and for rubbing, how do different parameters associated with the rubbing affect the flow rate. So here's a quick outline of my presentation. I'll be doing a phenomenon investigation, then a theoretical model, experimentation and discussion, and finally a quick conclusion. So let's begin with the phenomenon investigation. So in these 2 phenomenon videos, you can see the 2 different types of applied oscillations described in the problem statement. So on the left here, you can see shaking the pepper pot, and on the right, you can see rubbing an object along the bottom of the pepper pot. And you can see that with rubbing, the flow rate of mass out of the pepper pot is a lot more consistent and is actually greater. In fact, when we shook the pepper pot for 10 seconds versus rubbing an object along the bottom in this manner, and what you see in these videos here, we got almost double the mass discharge out of the pepper pot for rubbing as opposed to shaking. So a very important part of this problem is jamming. And jamming is the random arrangement of particles to form arches around apertures. And these arches are very stable and therefore prevent any further flow of mass through the aperture unless the arch is broken. And you can see that these arches form randomly. This is an experimental distribution we collected of when a pulse is applied to the pepper pot, how much mass comes out before the flow jams. And you can see in that video there that when we apply a pulse, some mass comes out, but then the flow is interrupted by jamming. And for this problem, oscillations like shaking or rubbing have the effect of disrupting jamming from occurring. And this means that there is a faster and more continuous flow of mass out of the pepper pot aperture without jamming. And the second key part of this phenomenon is the 2 different types of oscillation described in the problem statement. So first we have shaking, which is a very high amplitude but relatively low frequency type of oscillation. And it results in the particles moving around significantly within the pepper pot. And this means that they might not always be in phase with the pepper pot movement, and therefore that this is not the most effective method for achieving a maximum flow rate. However, for rubbing, which is the main type of oscillation being described here, is a much lower amplitude, a much higher frequency type of oscillation. The particles don't have as large of an amplitude of movement inside the pepper pot, and they directly receive energy from the oscillations via contact with each other and the inside walls of the pepper pot. And we can actually observe the phenomenon occurring by using discrete element method computer simulations. So this is a demonstration of jamming. You can see here, it's kind of hard to see, but a small amount of particles come out before the flow jams and the mass discharge stops. And here is a demonstration of what happens when you are rubbing an object along the bottom. You can see the flow rate is a lot greater and more consistent. And here's a demonstration of that where the color indicates the actual velocity magnitude of the particles. So basically a color closer to white, it's kind of hard to see with this lighting, indicates a greater velocity. So we can see the velocity increasing, turning more white as a result of rubbing. So we can see that rubbing causes the particles to gain kinetic energy. So now let's move on to our theoretical model. So we make three assumptions in our theory. The first is that there is a very small amplitude of oscillation with rubbing. So we can avoid acceleration correction terms like that expression for the effect of gravity. And the second assumption is that rubbing completely eliminates the effects of jamming. We assume that the continuous oscillation prohibits jamming from occurring, so we don't have to take it into account in our theory derivation. And the third assumption is that the only movement of particles is small amplitude vibrational motion and downward motion through the aperture. We do not take into account large amplitude oscillations like with shaking, and we also don't take into account any convection cells or other irregular flow patterns. And here's a quick overview of what our theoretical model describes. So we propose that the oscillation caused by rubbing transfers energy to the particles inside of the pepper pot, causing them to gain kinetic energy and move against each other more. And the more they move against each other, or the more particles are moving, the more the average interparticle friction is reduced, because more and more static friction is turned to kinetic friction as more particles begin to move. And this reduced average interparticle friction allows for an increased flow rate through the aperture, because kinetic friction is weaker than static friction. So we begin our theory derivation with the Beverly equation, which is commonly used to model the flow of particles through an aperture. And you can see here that W is the mass discharge rate of particles, C is a discharge coefficient, rho B is the apparent density of the particles, which is basically the density of the particles excluding any air voids between them. So basically just the density of the material itself. Capital D is the aperture diameter, lowercase d is the particle diameter, and K is a friction coefficient, which basically represents how hard it is for the particles to flow through the aperture. Think of it as analogous to viscosity if this were a fluid. A higher K would basically be analogous to a higher viscosity. And K will actually be the main focus of our theory derivation here. So we assume that particle energies follow a Gaussian distribution for the purposes of calculation here. And we further assume that there is a threshold energy value for the particles, which we'll call EC. Where particles have energy greater than EC, we assume that it is very likely that they have kinetic energy. So for the purposes of our theory, we assume that particles with energy greater than EC are moving, and particles with energy less than EC comprise the resting mass, the non-moving particles. And the energy input into the system from the oscillation due to rubbing increases the average energy of the particles, and therefore increases the proportion of particles with energy above EC, which have kinetic energy. And this means that it is easier for the particles to flow because there is more kinetic friction and less static friction between particles. So we can then relate this energy distribution to K, because we assume that the average energy of the particles is proportional to the oscillation frequency, because each oscillation should input the same amount of energy into the system. And we let A equal the proportion of particles subject to kinetic friction, the proportion of moving particles, and B be the proportion of particles that are the resting mass. And we assume that, once again, K is proportional to B, because the more resting mass there is, the more static friction, and the harder it is for the particles to flow. So we derive that mathematical expression for K, plug it into the Beverly equation, and obtain our governing equation shown here, with these variables on the slide. And for the purposes of our experimentation, we are testing three relevant parameters, which are the aperture diameter, the particle diameter, and the frequency of oscillation due to rubbing. So now let's move on to our experimentation and our discussion. So here's our experimental setup shown on the right there. And you can see that we have two pepper pots resting on each other with the grooves on the bottom in contact, and it's these grooves rubbing against each other that actually creates the oscillation when they're rubbed against each other. And the top one is filled with a large amount of sand in order to ensure that it applies a relatively constant force in the bottom one. And its motion pattern is restricted by the ring up there to ensure that it follows a constant motion path. And on the bottom we have a plate with interchangeable aperture sizes. And we perform this experiment manually, so a metronome keeps the time as we rub. And the rubbing follows this pattern here. We rub the top pepper pot around the circumference of the bottom one. And also an additional note, for ease of calculations and for brevity, from here on out the term frequency will refer to the frequency at which we rub the pepper pots, not the actual frequency of the oscillations created by the pepper pots, although these two frequencies should be proportional to each other, so that's covered in our experimental constants, which will fit. So our relevant parameters are shown here. We have our three independent variables that we've already covered. We have our dependent variable, which is the mass discharge rate, and we have our control, which is we always use sand, so there's a constant apparent density. And for each test condition, we know that doing the experiment manually introduces quite a bit of error. So we perform 10 trials of 10 rubbing revolutions per experimental condition to average the results and try and minimize error. So here's our first parameter being tested, which is flow rate versus rubbing frequency. And we can see that higher frequencies correspond to a higher discharge rate. However, eventually an asymptotical behavior is observed because at that point, enough of the particles are moving to where additional energy inputted doesn't significantly increase the flow rate anymore because they're all already moving. And the next parameter that we tested is the aperture size, D. And you can see here immediately that, that the higher aperture sizes result in a higher discharge rate, but there's quite a bit of error for apertures that are too large. But we expect this error because our model mainly takes into account the increase in kinetic energy as the factor driving the increased flow rate. However, when the aperture is so big that it's hard to even observe jamming with this aperture, then it's simply too easy for the particles to flow through the aperture anyway. So the increases in particle kinetic energy are not going to be the significant factor affecting the flow rate, and our model doesn't accurately describe it in this region. But in the region with smaller apertures, it describes the experimental data well with a power behavior because there's a 5-pass power in the Beverly equation. And we observe a similar trend for particle size. You can see that for a low particle size, where it's too easy for the particles to flow, our theory underestimates the actual mass discharge rate, but it approximates it quite well for larger particles. And so finally we move on to our conclusion here. So in summary, the elimination of jamming as well as the increase in particle kinetic energy as a result of rubbing results in an increased mass flow rate. And we can derive an equation for this, which is a modified Beverly equation, where we derive a term for the constant K. And as for optimization, again, the relationship of flow rate with regard to frequency was asymptotical. No significant gains in flow rate were observed past a rubbing frequency of 1.833 Hertz. And the flow rate increases for larger apertures and increases for smaller particle sizes. However, our model breaks down slightly when it is too easy for the particles to flow out. So for very, very low particle sizes and very, very large aperture sizes. So that is all. Thank you very much.
Can you turn to page 23?
23? Okay. Okay.
You say that when the hole is big enough, that the theoretical line will use on the data. So where is the certain numbers of the
Oh, you mean where's the separation between where the theory works and where it doesn't? Well, based on our experimental data for our particular sand particles, you can see it's pretty much somewhere between these two values. And basically, I think that in more physical terms, the cutoff would be around where it's hard to get the particles to jam flowing through the aperture, where the aperture is so large that it prevents jamming.
Okay, can you to page 9?
Yes. Oh, sorry. Yeah.
This robbing,
Yes.
a high frequency and small one, or
This is the rubbing, the high frequency and small amplitude. But this is just a computer simulation. In reality, the amplitude is probably a lot smaller than this, but this is just to visualize the effects of it. So this is not necessarily matched to our experimental conditions. That's why you see the particles actually vibrating vertically quite significantly.
so how will the paper build curve above the hole? Why will it?
No, I'm saying that with rubbing, it prevents it from building the arch above the hole, so that's why the flow rate is constant. There's no gamma.
I'm sorry. The opponent, you have 3 minutes to prepare.
Distinguished competitors, this is a woman from C3. Today I'm going to be recording paper pot. And here's the problem statements he mentioned before, so I skip it. About the summary of the report. About the theory, we talk about the jamming and type of oscillation and some formula to the theory, to the experience. And about the setup and experiments, he used paper pots to rubbing and the granular contents and change frequency of rubbing aperture size. Conclusion is rubbing causes particles to gain kinetic, and the advantage of the reporter is the clear setup and the clear theory and vivid PPT and the charts is done pretty well in the simulation. And the question for the reporter about the theory, I want to know the law and the formula related to the presentation more. And about setup, does the material of the Robin equipment affect the experiments, and in which kind of ways? About the experiments and parameters, how would you explain why shaking and rubbing will have quite different results? And does different hole size affects the experiments? Is the opening of the hole sloped on the side? Okay, and about the results, you tend to do the experiments or motor? Yeah, that starts. Okay, in page 12. Yes. What's the formula here?
Oh, that formula is just if the amplitude of oscillation is significant enough, then we would have to replace the variable g in here with that corrected value for g to incorporate the acceleration of the particles due to the oscillations. So basically what we're saying with this statement is that the oscillations are so small amplitude that they don't provide a significant enough accelerations for us to correct the acceleration due to gravity.
And why will the paper stop like this? Isn't there another shape of
okay, so essentially the phenomenon of jamming does basically state that the particles form a sort of hemispherical dome-like structure in order to limit the flow, because this is a highly stable structure where the static friction between the particles creates basically a very solid structure that is able to resist the pressure from the other particles pushing down. So I believe that is how the particles jam.
In page 50, what is this picture means?
Okay, so this picture is essentially an energy distribution of the energies of the particles in the pepper pot. And again, essentially what I'm arguing here is that there exists a critical energy value EC, where if the particles have an energy greater than EC, probabilistically, it is highly likely that they will be moving in half kinetic energy. And we can simplify this in our experiment to assume that particles with energies greater than EC are moving and are therefore governed by kinetic friction. Meanwhile, particles with energies less are static and are governed by static friction.
Does the material of the rubbing equipment affect the experiments?
So you mean the material that the pepper pots and the grooves on the pepper pots are made of? So you mean that the material that the contact point between the pepper pots is made of?
Yeah.
Well, in our experiments, the actual grooves on the bottom of our pepper pot were made of glass. Different materials for the rubbing equipment might affect the experiment because if the material, for example, just hypothetically, rubber provides enough damping of the oscillation, and the oscillations might not be as significant.
What's the surface look like?
The surface on the bottom of the pepper pot.
On the pepper pot.
Yeah. Okay. So on the bottom of the pepper pot. So basically, this is looking at the bottom. There's a whole series of grooves in the pepper pot, essentially indentations. And this is on the bottom of both pepper pots. So when the pepper pots are rubbed against each other, then the grooves interact, and basically, like route like this, the grooves of the top pepper pot are basically interacting with the grooves of the bottom one and pushing it up and down as we move the top pepper pot around.
But how big the gap is here?
The gaps, we didn't measure it specifically, the actual length of the gap, but we do know that on the bottom of each pepper pot there are 52 of these grooves. So that's the conditions that we use.
And when you turn the paper pot above, do you know how many times it shakes the paper pot under?
No, we did not measure that because we did not have equipment that could accurately measure the very small amplitude oscillations of the bottom pepper pot. However, I would assume that it is proportional to the number of grooves on the top of the pepper pot.
But if you know how many gaps here,
Yeah.
you can know when you turn a degree, you can know
Yeah.
how many gaps you go through. So you can know how many times it's shaking.
Yeah, so I think that is definitely a good point, but I cannot actually confirm this for certain with like experimental measurements, so instead I just use the frequency of my rubbing as the variable.
Another problem is, did you use hand to turn the paper pot above?
Yes, well actually I grabbed onto the pepper pot here, like around the pepper pot.
You grab the paper pot here?
Yeah, around there. And then the ring above is just to restrict the motion of the pepper pot to keep it in that circular rubbing.
Yeah, but how do you make sure you didn't make a pressure on the paper pot below?
Well, the answer is that there would be some pressure from my hand, but that's also why we fill the top pepper pot up with a lot of sand, because the force from that sand is the main pressure that's being exerted on the bottom pepper pot. The pressure from my hand should be less significant.
Okay. How? Oh, so you. Oh, okay. The frequency you mentioned here, is it related to the pepper in the bottom of the pot?
So you're essentially asking me if the frequency of oscillation of so the frequency of the rubbing is related to the frequency of the actual particles in the pepper pot? Is that your question?
I mean, the fastest dropping velocity.
Yeah.
Yeah, the frequency.
Well, this is my graph for frequency of rubbing, if this is what you're asking about.
And this is related to the how big is the okay, sorry.
Yeah.
I mean the bottom.
Yes.
And the bottom have some little curve.
Yes.
Would those curves affect the frequency the paper drops?
Well, as I already stated, perhaps I should clarify this. This value represents the frequency at which I'm rubbing, and this frequency should be proportional to the actual frequency of the oscillations of the pepper pot with the proportionality factor being the number of grooves here. And the only reason why I didn't include that on the x-axis here is because I wasn't able to confirm that experimentally. So I just used the frequency at which I turn the top pepper pot as the x-axis value here.
Another problem is why don't you change the other the variable in this formula?
Because those are very hard to change experimentally. Those are actually more dependent on just the properties of our set. So what we actually did is, you can see here, when making our theory curve, the red curve is our fitted theory curve, we actually just fitted these values to our experimental data. So our approach to those values is more to fit them than to change them.
Also, when you do the experiment, you set down all the other variable in this formula.
Well, essentially, yeah, we predict that those other values would be constant across our experiments, and how we determined those values was, again, by mathematically fitting our model to the experimental curve and obtaining these fitting constants there.
Is the opening of the hole sloped on the side sorry. Does different hole sizes affect the experiments?
Oh, absolutely. In fact, this is the next figure in my presentation. Sorry if this wasn't clear, but the aperture size is referring to the size of the hole. This value in the x-axis is the diameter of how big the hole is.
Okay, I think that is.
Okay, thank you very much.
The opponent is summarized in the discussion.
The reporter done many variables in this experiments, like the size of the hole, and he mentioned the other situation instead of just saying this kind of dropping. He said he mentioned many oscillations in his reporter, and his charts is done pretty well. About here, he said he mentioned clearly why will these two dots will not fit the theoretical line, and I think reporter done a pretty good job. Thank you.
Reviewer, please.
So I have a few questions for the reporter.
Okay.
So as we all know that the paper parts have lots of hole on it. So why did you do your experiment just in one hole on the paper part?
So I did do my experiments with one hole in the pepper pot. I covered up all the other holes. But if you're asking why I didn't use multiple holes, well, the flow rate should just increase with the number of holes proportionally.
Okay, so do you think the vibration between them will be different?
No, I think that the experimental results should still hold true if there are more holes. Just the
Okay.
yeah.
So thanks. And what's your opinion about when the hole is increasing? Just we all know that the paper part has a lot of hole on it.
The flow rate will come bigger.
So it will be different, right?
Yeah.
So okay. And can you explain why the rubbing frequency and the oscillation frequency have a positive correlation?
Well, that's just because, similar to what the opponent pointed out, the frequency at which I rub the top pepper pot should be proportional to the frequency of the oscillation, because the proportionality factor should be the number of grooves here. In other words, when I turn it a certain number of degrees, it depresses a certain number of grooves and it creates a certain frequency of oscillation. And that should be proportional. I just didn't experimentally confirm that, so I didn't put it in my graphs.
Okay, so do you know that what the what friction is on the between the pepper pots is the static friction or the kinetic friction?
Well, kinetic friction because I'm moving the two pots against each other. They're moving when I'm rubbing them.
Okay, so what's it in your you use a DEM to show us the vibration of the pepper pot, right?
Yes.
So what's the difference between the simulation and the real life
Well, the only difference there is that we didn't actually have time to use the simulation to visually represent our experimental conditions, but the simulation should still accurately represent what happens. It's just that, for example, the amplitude of oscillation shown would probably be different from our experiments.
Okay, so opponent, what's your opinion about the simulation and the real life condition?
In real life condition, maybe we should take air resistance or something into consideration.
Okay, thank you. So this is my question.
Thank you.
有没有拔掉？有拔掉。
Okay, hello everyone. I'm a reviewer from MD French. So my name is Cho Hong Bin. And so first we take a look at our problem statements. And so if you take a paper pilot or salt pot and just shake it, the contents will pour out relatively slowly. And however, if we rub it, and it will the pouring will increase dramatically. So we investigate this phenomenon in next page. So first we overview our reporter, and the advantage is he has a clear focus information about the phenomena and a low role explanation about the theory, and he distinguish the different situation with obvious comparison, and he complete quantifications with relevance variable equation. And my suggestion is he should have a better explanation about the rubbing effects on this rocks jamming, and elaborates on the application of variable equation. And he should consider using motor instead of handling operating mechanism. So next page. So overview of the opponents. that his advantage is he clarifies the problem statements by phases. And my suggestion is he should multiply fundamental questioning and make a deeper encourage on singular topic, and he needs to express his own opinion about each question. So, and in the discussion one, the opponent asked the reporter how was the cause of the jamming, and the reporter said that the static friction caused form of jamming. So, from my perspective, I think it requires more explanation between the variations of loss formula to this experiment so that we can know this more clearly. Next. And in the discussion two, the opponent asks, but how was the coefficient determined? Aren't those also important factor? And the report shows the theoretical line which goes up a certain value, and they fitted the coefficient according to the result. So I think I will support the reporters. Yes. And in the discussion three, the opponent asks what does the surface look like, and the reporters drawn on blackboard and describe visually how the grooves contact. So I think the difference of material on groove of parts will impact this experience. So it needs more experience. Yes, thanks. And the discussion four, the opponent asks the frequency of motion should be measured and considered, but the reporter did it, but from their theory, it's them. But I think they should do many measurements of frequency of the oscillating pepper parts. So next. So this is our conclusion. So I think the reporter should do a more measurements of their each parameters, and we can know this experiment more clearly, and the opponent should ask a more deeper question so that I can use this more yes. So this is our presentation. Thank you.
Thank you. So concluding remarks from please.
Okay, so thank you to the reviewer and the opponent for your questions and suggestions. I'd just like to clarify a couple of things. First of all, the reason why I'm able to use the frequency of rubbing as the parameter here is because I believe that that is proportional to the frequency of oscillations. However, they mentioned several times, the reviewer in particular mentioned that I should attempt to determine this, but the problem is that the amplitude of oscillation is so small that there's no accurate experimental way to do this. In fact, it's so small that it's not even visible via video tracking. Visible even to the eye. So this would be very difficult to do, so I just use the frequency of rubbing as the parameter here. They also mentioned more parameters could be tested. I agree with this, and they did mention that one of those parameters could be the material of the grooves. The grooves, as stated earlier, were made of glass for my setup. However, I think that different materials could have an impact on the flow rate due to potential damping of oscillation associated with certain materials. And finally, multiple times it was asked why I did not use a motor for this setup, and that actually has to do with the material of the grooves. I did attempt to use a motor setup, but I found that because in order to connect the motor stably, it had to apply a really high amount of pressure between the grooves. I found that the motor actually wore down the grooves very quickly, so that was not a sustainable method for experimental testing. So I decided to use a manual method because it actually allowed the grooves on the bottom of the pepper pot to not be worn down as much because there wasn't as much pressure applied onto the pepper pot. So those are my concluding remarks. Thank you very much.
Okay, thank you. So question from the jury.
To gain a deeper understanding of this phenomenon, I wonder if anything will change by assuming that horizontal way of vibrating rather than vertical. In your model, you assume that it is the rubbering induced vertical vibrating, right? How about horizontal mode?
Well, I do think that especially since we're rubbing around the circumference, so we're changing the horizontal position of the top pepper pod, I do think that there would be some horizontal oscillations here. However, I think that this is partially accounted for in our model because our model mainly focuses on kinetic energy. So kinetic energy of all types, so vertical vibrational kinetic energy, horizontal, those are all encompassed by our models. So I do think that I could modify some of, I think, our theory adequately covers.
You are saying that it would be all, equally effective to pulling the pad out?
Yes, I do believe so. It would be about equally effective in disrupting jamming, and our theory could model this quite well.
How about the opponent opinion? If the rubbering creates horizontal vibrating rather than vertical, or would that be also having the effect of pulling a lot of pad out?
Yes, maybe. Yes, I think the horizontal burst vibration will also affect this experiments. That's because the peppers use this shape, right? So we just destroyed this shape, so that makes the pepper falling down. So when we destroy we use a viscous, and use a horizontal vibration, and it will break this shape. So that makes the pepper falling down. So it will also affect this experiment.
Okay.
You go to page 15.
Okay.
What's F? What's F? F is F. F is the probability of the particle passing through the
F is just the equation describing this Gaussian distribution. So that's just describing the
physical meaning of the F. What is that?
the approximate amount of particles that have a certain given energy along this energy scale.
Is that density or what?
A proportion. So a certain energy value F states the approximate proportion of particles that have that energy. So we're using that to find the proportion of particles that have kinetic energy and the proportion that do not have kinetic energy.
And what? And we go back to the page 22.
Okay.
If the EC is minus 2.7,
Yes.
why?
Well, this is actually a relative value because earlier we stated that the average energy of the particles is proportional to the frequency. So we arbitrarily set the initial average energy to 0. So basically what that means is for negative values, the physical meaning of a negative value on that scale is that it has basically 0 energy. So we're basically arbitrarily creating this scale. We're not attempting to state that particles have negative energy.
You think that's true? If the energy is negative, minus 2.7.
Well, I mean, on our scale determined for just the purposes of calculation, there could be negative values. Physically, those would just be particles that are not moving at all. I mean, this scale is arbitrarily created for our theory. It's not attempting to actually state that they have negative energy.
You use those values for the fitting in page 23?
Yes. The same values are used.
Oh, identical values.
Well, I mean, the same fitting.
P, A, K, F, and C, all the same.
Yes, yeah, they're the same between our fittings. So, yeah.
So could you go back to page 22?
Yes.
Could you give us an explanation why you see this saturation of flow rate when the frequency increases?
Okay, so because we're saying that if a greater proportion of the particles in the pepper pot have kinetic energy, then the flow rate increases. Well, eventually there will come a certain frequency where the energy input from the rubbing is so great that practically all the particles have kinetic energy at that frequency of rubbing. So therefore, increases in the frequency of rubbing and the energy input would not cause a appreciably greater amount of particles to have kinetic energy, since almost all of them do. So there's no significant change in that proportion, and there's no significant change in the flow rate.
Okay, can we start? So the whole scope. So let's start from the reporter. Please. Okay. 777988.
Thank you.
Opponent, please. 544 666. And reviewer, please. 576767. Okay, anyone want to make some comments? No? Then, okay, let's take a 10 minutes break. Start the next one. Also, I want to ask each team write your names on the blackboard.
你刚才找脚趾，大家都会吓到，大家都每次跟我说，直接一直都说回来。哦，这个是学姐吧？应该是毕业学姐。自动。为什么毕业学姐今天毕业了？然后对，尽量就塞在第三期需要比较多。
Okay, hello everyone. My name is Mei Chen, and my team is VD, and I come from Gangwon High School. And my topic is Sinfera. The first is problem statement. This important part is at some frequency the rod begin to produce a sound. So we have a problem is if we want to the magnetic coil produce a sound, which current should be used? And my opinion is choose the magnetic current because of the problem statement say at some frequency. And this is my main idea. Changing the declaration of current and it will cause changing magnetic field and then it will cause the produce a sound. Okay, it is a principle. I give this topic further explain. When we input a magnetic current in the magnetic coil, it will produce a magnetic field, like this figure. And the experimental research, this name is called magnetostriction. And this video is symbolized as a hermetically reversed declaration. And this is at station frequency. And this part is changing the declarations of magnetic field. And the magnetic field will change rapid between left or right. And this is a theory list. The main theory I use is these three. And Barkhausen effect, magnetostriction, and the magnetic domain. And what is a Barkhausen effect? A Barkhausen effect is its theory under it is magnetostriction. And the theory under magnetostriction is magnetic domain, magnetic saturation, and magnetic hysteresis. Theory 1, magnetic domain. Barkhausen effect, sorry. The Barkhausen noise is act on the magnetic material. And when we apply a magnetic field, it causes change of magnetic domains. Reason A is microstrand, and this theory is magnetostriction. And B is crystal locate defects in the lattice, and this theory is magnetic domains. So what is a magnetostriction? It is a property of ferromagnetic materials that cause them change their shape during process of magnetization. And this formula, the lambda is a magnetostriction coefficient, and this is a propagation, and L is the origin length of the material of the rod, and the delta L is because microstrand length. And the Barkhausen effect, it will produce a low pitching humming sound. And low or high I will talk later. And it can be heard some coming from transforms, whereas magnetic currents produce a changing magnetic field.
And what is a magnetic domain? When a magnetic field is applied, a balance between the domains shift and domain rotate. At page 18, I will tell that. Most of this effect causes a change in material's shape, and it's, I said before, magnetostration. Okay, magnetic domain, the reason is crystal-related defects in the lattice. And this wall is called domain wall. When we apply a magnetic field, this will shift, and when we meet the crystal-located defects, it will change the shape between the left or right. And this change will cause the magnetostration. And this is a theory I don't use because if I have time, I will put it in the end of the topic. And what is about thin ferrite I focus on. The one is frequency of magnetic current and microstrand. And second is frequency of AC and the frequency of the sound. And I haven't decided to do an experiment about measuring magnetic test. Okay, it's my experiment. This is the procedure. It's my experiment. This is a AC power supplier, and in the middle is magnetic coil, and on the right is ferrite rod. And my experimental setup is, this is the frame. It's my experimental setup of, yes, it is like you see. And the right is ferrite rod inside the magnetic coil, and I use a knife to hang the rod. It is because avoid it attach the coil. That's the simple picture this. But I think this experimental setup is not perfect. Why I said is because it has error because of surrounding vibrations. And my solution is because this can be reduced with a proper vibration isolation. This means I can reduce the later influence of the sound. And this is my experience setup before. And later I put a soft mat to reduce external interference. And it is inside. It's like this picture. We use a knife to hang the ferrite rod. And how about our AC machine? We put it on the floor, also to vibration isolation. And this is my measuring tools. And this I don't use, and if I have time, I will tell in the end. And this pointer and accurate level theory is my way to measure the magnetostration displacement. Magnetostration, and as I said before, and magnetic field strength, I use the app to measure it. And value of current, I can see the machine of the data, I can know it. And this is analyzed ways. I will use a density FFT analyze and Excel. And this is our level theory setup. If everybody wants to know, can ask me later. And it's like this picture. And my experiment. To find out the connection between the frequency of AC and microvibration. And the second is frequency of AC and the frequency of the sound. This is our setup. And this is the chart. I will say it in the analyze. And the chart I transform the propagation because maybe somebody will thought this value is too sharp, so I change the propagation. Second is frequency of AC and frequency sound. And this is definition. And the first is different lengths, 20 and 25 centimeter, and the other is control the same radius in 1 cm. And this is the track. The second is change the different radius, 1 and 1.5 centimeter. And this is our density of our track. This is the FFT analysis. So we can see the peak value on this chart, and its frequency is 760. And I will discuss with the analysis too to find more connection. Okay, it's length 20 and 25. And on this page, we can know as the rod length decrease, the frequency of the rod increase. And this is a different radius of the chart. We can see it's not connection in this chart. So look our density of the chart. It is a noticeable change in frequency of the rod. Check the microration chart. I think it is the right answer. And this frequency is 750 to 780 hertz. So when we look the chart of displacement, you can look the peak value. Its frequency is 760. And something is referred on the microstrain chart. Maybe it acts resonance. Why I say this? Because when frequency of machine is same as frequency of the rod, it means resonance influences the microstrain of a ferromagnetic material. About hum sound, I said before the low or high sound is on this page. The high frequency of AC, the sound listen consistently. Humming is not obvious, and other is like this page. So conclusion is both belong to background house noise. Both of these are. So my conclusion is high frequency vibration are more effective at producing sound. The radius of sample do not influence the sample natural frequency. And the other conclusion is the resonance. And how about micronatostation? This is a segmented diagram, and it's a crystal locate defect. You can see on the left, it has more crystal locate defects. So the right one is fewer crystal locate defects, so it is suitable for the micronatostation. The more, I haven't used some properties like magnetic. If I have more time, I will produce more about it. Thanks for listening.
Opponent can have some question.
Okay, so first of all, you said that you're going to talk about the theory. You're not going to talk about the theory as long as someone asks you, so can you explain it now?
Which theory do you want?
The one you skip.
I skip it is magnetic. Okay, we can see here.
The one you skip, you said you explain as long as someone asks it.
Okay, this is a magnetostration hysteresis loop, and it also shows relation of magnetostration coefficient. And this I don't say because it's a little difficult. It's approximately a linear relation on this chart, and the y-axis is propagation, and I call it a magneto propagation, and the y-axis is magnetic field strength. And I have made some derivations on this page. And because it is a linear relation, so I set a constant of proportionality on it's minus k, and this formula is I use.
Oh, okay, that's it.
Oh, okay.
And
next question is, have you ever think about consider the temperature in this experiment? Since I guess that during the process of the ferrite rock turning, I think the temperature might increase. So, what's your opinion about
You
just
mean-
short question,
Oh,
short
okay.
answer. Does it affect? Yes or no?
Because the sound is the rod, not the coil. So if the coil temperature is higher, okay, it may, if the temperature rise, it may have some influence of the sound.
Okay, hi, I'm the opponent from MD Fresh, and now I'm going to oppose about problem 4, saying per. Okay, so let's take a look at the problem statement again. We think that the main point of this problem statement is that you need to determine at some frequencies and the rod begins to produce sound. That's the most important part of it. And first I will summary the theory of the reporter. The reporter mentioned about Buck-Hansen effect and magnetostriction, but what he says is that the magnetostriction is not so important. It plays a minor role in this experiment. And what he focused on is other parameters that he thinks will affect this. And I think his theory doesn't, his experiment doesn't really fit with his theory, since his theory is only talking about a qualitative description instead of a quantitative one. So we can actually match these two together and get a better description of the phenomenon. As for the experiment setup, the reporter uses a coil and a ferrite rod and other lines had whatever a very complex setup. I think that is a very good setup. And as for the parameters, I think he mainly focused on the radius of the rod and the length of the rod. However, the data he provided, I think, is just too few for me to really understand what he is doing and trying to demonstrate to us. The advantages for the reporter is that he described the cause and effect of the phenomena precisely and explained with helpful gesture. Sure, but I think that needs more. However, there are some suggestions from me to the reporter. I think you need to describe the concept more accurately and reduce some pauses when reporting. Just make it more fluidly. I need to reduce unnecessary words. You need to set the keywords to make us able to understand what you are trying to express. And you need to improve the time control since some unnecessary words you talk about too much. So as for the theory part, you take all of my time to explain it to me. Okay, the structure of the discussion. First, I will do some clarification of the theory, and then I will propose some question about the setup and the experiment since I misunderstood or curious about why it's doing like that. And some other parameters like that affect the result of the experiment will be discussed during my presentation. And then let's go through our discussion. Okay, so first of all, I want to talk about the theory. And the first thing is that in your report, you show that there is a, do you think that there is an oscillation of the parallel rod when, do you think there is an oscillation?
Yes.
And in your opinion, what does this oscillation affect your results?
The result of this or the theory of this.
What? Can you show me? Okay, so let's move.
This question I can answer you with.
You can answer me. Okay, next question. So you said that the oscillation affects. You said that there is oscillation. So what do you think that caused the oscillation?
Because we apply a AC current into a magnetic coil, and because magnetic current will change its direction of the left or right, and it will let the magnetostriction happen, and it will let the change the shape of the magnetic field or domain wall, and this causes the sound and its microstrength.
Okay, so moving to the previous question, do you think oscillation affects your experiment? Just show me what you think.
Okay, see this page. You say the oscillation transform between and the theory in this question is the crystal locate defects, and it means is if fewer locate defects, it will suitable to happen the Bartholin effect, and it's my plan.
Okay, so for the next question, we believe that there is resonance happening during the experiment. But in your report, you just tell us that there may be resonance. So can you describe more about the resonance?
Oh, Okay, it is analysis of of the ferrite rod sound, and we noticed about the frequency is very near the displacement of the frequency we put the AC current.
So how do you use, let's say, a theoretical formula to calculate the natural frequency of the rod?
This is not the natural frequency of the rod. This is the current we input, and the sound of frequency is, so it is a vector sound, and because the analyze we got the result like this.
So how do you know the resonance happens or not?
Because I do the experiment and I see the data and the result of those, and I think what is the effect behind, and I thought it may.
Okay, so it's only based on experiment data and observation, not a calculation or an exact theory.
This may be the next experiment I will to find it.
Okay, so in my opinion, I think you didn't really talk about the effects of the oscillation, and I think you need to figure out what is the natural frequency. Since you said that when the frequency of the input AC reaches the natural frequency, will create a resonance, which really affects the sound that is produced. So I think you need to really calculate it. Okay, so next part of our discussion is your experiment setup. And first of all, can you turn to the page of your setup with path and lines? Next page. Next page. I mean, let's set up. The one with lines and paths covering. Yes, this one. Okay, so I'm curious about this setup. And first of all, my question is, does those lines have any effect on this experiment? Since I think through my observation, you tied lots of strings on it. So, in my opinion, I think that will affect the sound, the sound the rod produced a little. So, how do you ignore this thing, or how do you correct it?
The first thought I want to do this because we need to avoid the rod to actually other things. So I use the line to hang it. I think it is the best way to reduce the external interference.
Well, I'm now asking that it's simple that if you attach something to the other one, it changes the sound that it goes. It's just like when we are playing drums and we touch the drum, it will stop to produce a sound. And in this experiment, you put strings on it, and it absolutely affects the sounds that produced. So how can you correct this? Okay, next question. So, and previous one. I want to see the previous one. Oh, previous one. Next one. Yes, this one. Okay, so why do you attach these mats outside just put these mats outside your experiment equipment? What is the purpose of it?
Because in the lab it is many sound outside, and we put the cell phone to record the sound in this setup. So we put the software is in order to reduce the lab noise of it.
Okay, so do you think that these soft mats can really effectively absorb the other sound or the reflect of the sound itself produced?
This is I agree, and I think it actually has a more better material to do this, and we just put the soft mat and in that time I just do that, and after I do this experiment, I can find the other material to increase the defense effect of it.
Well, in my opinion, I think that this is not a very good set up. I think you should maybe consider a place more like a concert hall. Yes, I think that kind of wall surface is much more effectively absorbing other sound. And then, okay, so in your experiment setup, as I see here, I actually couldn't see what is inside. So are you making sure that the rod is always inside the coil?
Of course.
So do you think that if it's outside, is there anything that will affect the results? If the rod goes outside the coil?
Because outside it just increase the difficulty of recording the sound, and this actually can do this experiment too.
You mean it's okay if the rod is outside the coil?
But when we want to analyze the sound, it will more difficult because have other noises of it.
Well, I mean just outside the coil.
Outside coil.
Yes.
And it can't outside the coil. It will not affect the magnetostriation.
And finally, the question I mentioned, I think that during the vibration of it, the temperature might change. And how do you correct the change of the temperature, or use your experiment data to prove that the change of the temperature affecting this can be ignored?
Okay. The temperature will affect the sound. I agree.
Yes.
Yes, John.
Yes. So how do you correct it? Because since the vibration will definitely cause a rise of the temperature, right?
Yes.
So how do you correct it?
When we do start to do the experiment, the temperature is not increased so high, and we can just record the first sound of the experiment at the start, and we can let the coil not input a current for a moment.
Well, in my opinion, I don't think he has proof to prove that this can be ignored. So maybe he should do some experiment to prove that this can be ignored. And thank you.
Okay, hold on, please summarize.
Okay, so throughout discussion, first we talk a little more about the theory. And for this part, I think that oscillation and resonance are very important. And the reporter didn't really talk about the conditions of the resonance. He only used experimental data to observe and said, oh, maybe here is a resonance, and which I think is not so good. And for the experiment setup, I think that setup has to be improved, since there's no proof that those masks can really absorb the sound outside or absorb the reflect of the sound produced by the rod itself. So maybe he should consider a more accurate environment. And as for experiment data, I think he just simply needs more data to support what he says and fit his theory more properly. Thank you.
Okay, question from you.
Thank you, reporter and opponent, for your discussion. Reporter, did you measure the background noise while you're doing the experiment?
The background noise I use Audacity is a software, and it can reduce the noise background.
Alright, then did you verify if the magnetic field in the coil is uniform? Yes or no?
I don't do about the magnetic field experiment. I said that before.
Opponent, since the rod also vibrates vertically, how do you think that would affect the sound produced?
Well, as long in his report he didn't do any, but I think it really affects the sound that produced.
Do you think the sound will be higher or lower?
Well, I guess it will be a little bit higher, but I don't have any data to say that.
How about the recorder? If the rod vibrates vertically, how do you think that changes the sound? So since the rod also vibrates vertically, because of the rotation of the organs. How do you think that changes the sound of the rod? How do you think that contributes to the sound?
The changing the sound is, I said, it's because when the changing is rapidly, quickly, and it will make the sound before it, if in the low frequency, it will like humming sound. But when we increase it to a high frequency, the sound will like constantly.
Do you think the strings will dampen the vibration of the rod? Do you think the strings holding the rod will dampen its vibration?
Yes, definitely, since they are attached.
And then how do you think that would affect the sound measured by the microphone?
Well, the frequency of it obviously will change, and the strength, the volume of it might also change too.
For your rod, you hung the rod partially outside of the coil. How do you think that affects your experience?
The length of the rod is a different kind of rod, and the coil is set up and is a steady of current.
Can you go your 2 minutes?
You mean come here because you can't pull it?
出去嘛，他延长就在这。
这是他给的。
右边那边。
哎。
等一下，他贴在地板上。
哦。
所以不能再来。
他要来这里了，所以他要来这里。哦，他们可以，哦，那好。
Good afternoon, I'm Austin, and today I'm reviewing scene ferrite. So this is a problem statement, and the focus is, first, why does the ferrite rock produce a sound? Second, what are the characteristics of the sound produced? And third, what are the relevant parameters that affect the frequency? So the reporter, he started with a phenomenon. He observed that there is a low pitch humming sound, and this is due to the changing field in the coil. And he used magnetic restriction to explain why the rod vibrates. And in a way, microscopically, the magnetic domain rotation causes the shape to change. For his experiment, he tried to use damping mass to reduce background noise. And one thing he did pretty well was he tried to use a laser pointer to analyze its displacement. But I think for his experiment, he tested little parameters, and some experiments had little data points. The pros are he had clear conceptual explanation, good experimental setup, clear speech, but It did not present a quantitative model, and there were too few variables to be tested and poor time management. The opponent clarified the theory and then also questioned on how to improve the experimental setup. And he also discussed other parameters. I think he had good time control. He offered his own opinions and focused on the experiment. However, I think there was a lack of emphasis on the math behind the theory, and he did not focus on the experimental data. Okay, next slide. So the first discussion was the opponent asked, how does the oscillation of the ferrite rod relate to its sound? And the reporter said the AC current changes the shape of the rod and the rod vibrates. But then the opponent added that this is because of mainly resonance and the frequency matching the natural frequency of the rod. I think the reporter could derive a mathematical equation that could predict the natural frequency of the rod. The second discussion was, do strings affect the sound of the rod? And the reporter said he used strings because they're meant to stabilize the rod. And he believed that is important. And just like the opponent, I think the strings may cause damping. And because of that, the frequency of the rod will be lower. This third topic is the purpose of the damping max. And the reporter said it's to reduce background noise from outside. And the opponent said we could consider testing a concert hall. But I think simply measuring the background noise can make the experiment much more easy. And lastly, they discussed how does the temperature affect the sound because of vibration in internal friction. The reporter said the change in temperature will affect the sound, but I think in the internal friction, the magnetic force between the domains are way greater than the internal friction between the domains. So I think that largely would not affect the vibration of the tube itself, and there's really little change in temperature to affect the frequency. I think some points they miss is, since the domains are rotating, they may induce a transverse wave or vertical vibration on the rod. And maybe they could derive a quantitative model for its resonant frequency. And I also think they focus less on the photo itself and how that changes the sound. All right, thank you.
Okay, thank you. And concluding remarks from the reporter.
Okay, the string doesn't affect much, and the software at my new setup could keep the noise from affecting the experiment. Shorten the time of experiment, ensure the change of temperature doesn't that much. So that effect of temperature could be minutes. And I want to say the length of the rod is affect the frequency of the sound. When the length of the rod is long, its frequency is lower, and when the length of the rod is shorter, the frequency will higher. And the radius of a ferrite rod is not affect the frequency, because same material is natural frequency is constant. Okay, that's all.
Question from the field.
Frequency. What's your driving frequency?
Frequency of
700, 760.
in the analyze of the sound, the frequency is the analyze is the sound like natural frequency of the material rod.
No, I ask you what is the driving frequency for your coil?
Coil.
Yes.
Electric current.
Frequency for the coil. What is the frequency?
Frequency is the direction of the current change the.
700, right? And why do you have a frequency measured at 6 kilohertz. You have a FFT analysis, and there is one, or there are two, based on like 6 kilohertz, 4 kilohertz, 1.
Before I have a formula is not just pure, but this chart is I make it easy of it, and just point.
Yes, this one. Why do you have 6 kilohertz signal? Your coil is driving at 600 or 670 hertz, right? And you have FFT analysis at 2 kilohertz, 6 kilohertz.
The x-axis on the displacement, the first is about the alternating current, and this is the sound of the ferrite rod producing.
The reviewer mentioned about the transverse wave, and actually there's also the longitudinal wave along the rod. So I would like all the three teams to comment that how do you think about the transverse wave will affect your observation? Do you think the transverse wave is important? If yes, and how will the transverse wave change your result? What else you will observe? One by one.
Can we change the, let's see.
I think for the rod, generally it's harder to bend the rod than to stretch the rod. So when a rod is harder to bend, that means that when it resonates, the rod will vibrate at a higher frequency. So a transverse wave will cause us to hear a higher frequency, and the longitudinal wave is still there, so it will also have a lower frequency. So we will both hear a low pitch and a high pitch.
Well, I think the transfer wave of the rods may also affect the frequency of the sound. However, higher or lower may depend on the specific condition.
On the higher frequency, the longer of the rod, its frequency is decreased, and the shorter of the rod, its frequency is increased.
Any others? Okay, I want to ask one question for you. Did you heard this sound? Did you heard this sound? Have you heard very small? Can you did you record the sound? Yes. Can you show that? If you record this. Okay. Okay, never mind. Okay, never mind. Let's go. Let's go. Okay, let's start from the reporter. 56555. Then opponent 666766. Then reviewer 878677. Thank you, everyone. Make sure you want to make sure. Okay, so no question. Let's close this round. So thanks everyone. Okay.